Hello everyone. Now, in this second part of the first module, I will be talking about PE gel fibers. PE gel fibers are nothing but ultra strong, very high modulus fibers which are produced from flexible polymers like polyethylene, and the process by which these are produced is known as gel spinning. So, we will be understanding what is gel spinning and how do we produce such fibers. The regular polyethylene fiber, which we all are aware, is produced by melt spinning, and it has a structure which has highly folded structure, large amount of rubbery material, quite low orientation, and the crystallinity is also less than 60%. These materials have been known since 1930s. Now, the high performance polyethylene, how do we make that? And if you know, the high performance polyethylene actually came into being only in 1980s. That means, after 50 years of the regular polyethylene. What does that mean? Isn't it surprising that it has taken scientists almost half a century to actually straighten a polymeric chain of polyethylene? So, these materials are produced by creating a structure in which the polyethylene chain is highly extended and it is aligned along the axis of the polymer fiber. When we do this, the crystallinity of the fiber increases up to 85%. It has very high degree of orientation and almost minimal defects. So, this is what is actually contributing to the high performance properties. Now, the low defects, when I am saying low defects, so what is the factor which would actually control the defects? One is the polymer chain ends. That means, if I have a polymer with low molecular weight, I am likely to get more chain end kind of defects, and if I have a high molecular weight polyethylene, then there will be less number of chain ends. So, that means, one way to reduce the chain end defect is to use high molecular weight polyethylene. Am I right? Do you agree with me? Yes? Okay. So, that means, I have to look for polyethylene which has very high molecular weight. It will not only lead to low defects, it can also be used, it can also be more suitable for drawing it to the higher degree. So, if I am using ultra high molecular weight polyethylene for reducing the defects, then the problem is the melt spinning of such a polymer is not possible. Can you answer why? Can anybody tell me what is the possible reason for not being able to spin it by melt spinning method? Right. The main reason is it has extremely high melt and elongational viscosity. Very high melt and elongational viscosity is because of the large number of entanglements which are there because of the high molecular weight. So, if I try to melt spin this fiber, I will not be able to get super drawing. I will not able to create a structure which has got polymer chains extended along the fiber direction, however much I draw it. The as-spun fiber itself will be so highly entangled that in the subsequent frequent drawing process, it will not be possible to remove these entanglements and draw the structure. At the max, I may get a highly folded structure. The polymer chains may be oriented along the fiber axis to some degree, but not extended, right. And what we need is extended polymer chain structure. So, what do I do? How can I create such a structure where I do not have folds? It is possible only if I have optimum number of entanglements, because you noticed it is the entanglement which is causing a difficulty in stretching the fiber, in bringing it to an alignment along the fiber axis. So, what do I do with the entanglements, and what is meant by the optimum entanglement? Optimum entanglement means I should only have the entanglements which are necessary for me to process the fiber. I do not want the number to be more than what is required. Only under these conditions it will be possible to draw the fiber to the highest possible extent, what is known as the super drawing. So, that means I need to spin the fiber from a state in which there are optimum number of entanglements, and generally this state which we say is a gel like state. In this state there are optimum number of entanglements, and these optimum number of entanglements allow the load transfer during the drawing process, and they also help in controlling the crystallization. So, the requirement, as I say, is optimum value of entanglements, and the moment I have optimum value of entanglements, I will be able to draw it successfully to obtain very high draw ratios and remove all the folds and entanglements and create or align the polymer chains along the axis of the fiber. Is that right? Am I clear? Yeah? If anyone has any doubt? Okay. So, do we proceed further? Fine. So, now having known that we need optimum entanglements, let us understand what is the optimum value of entanglements. How many entanglements do I need? How do I know that? Let us see a simple case. If I have two polymer chains, right, and I need to transfer the load from one to the other, what do I need? How many entanglements do I need? One, right? There should be one entanglement. So, that means if I have three polymer chains, then how many entanglements? They should be connected at two places. If they are connected at two places, all three are connected. The load can be transferred from one to the other, right. So, that means if I have n polymer chains in a system, then there should be n minus 1 entanglements, right, and n is very, very large in a system. There will be infinite number of polymer chains. So, n and n minus 1 are almost equal, right. So, that leads to the point that I need one entanglement per chain. So, if you have one entanglement per chain, that would be theoretically the optimum value. How do we look at it theoretically? Theoretically, we define what is known as critical concentration, C star. Critical concentration means it is a concentration at which theoretically the polymer chains just begin to overlap. That means there is just one entanglement per chain, and this critical concentration is proportional to ME divided by M. Here ME is the molecular weight between the entanglements. It is depends upon entanglement molecular weight is a property which depends upon the nature of the material. More flexible a polymer, the lower will be the entanglement molecular weight. That means, it is more easy to entangle, right. More rigid a material, it will be less probable for it to entangle. And the molecular weight, if you have higher molecular weight, then you will require much lower concentration. So, that means, the critical concentration is a concentration which is proportional to the entangled molecular weight, and it is inversely proportional to the average molecular weight of the polymer. So, from this relation you know, if I am using a very high molecular weight, that means my concentration, my critical concentration or the concentration at which I need to spin for getting such a structure would be very, very low, right. So, it would be, that means very high molecular weight and very low concentration. So, at this critical concentration, we are able to draw it theoretically to the maximum possible degree. Am I clear? So, do you all understand what critical concentration means? So, that means we need to play around with the critical concentration to control the entanglements. Okay? But the actual spinning is carried out at slightly higher concentration than the critical concentration. Now, you all may wonder why, because we have done so much of effort in calculating the critical concentration, and now I am saying we carry out the spinning at slightly higher concentration. Can anybody think of the possible reason? Yeah, I can give you a clue. You can think of what happens during crystallization. During crystallization, some chains come out of entanglement. There is disentanglement process that occurs. Some of the polymer chains, while crystallizing or while coming to the ordered stage, when they are in the entangled form, they may just fold, right, to come to an ordered form. In that process, some of the entanglements may be lost. So, if I have exactly calculated one entanglement per polymer chain, then the number of polymer chains which become disentangled, they will not be connected anymore, right. So, that means they will not be able to help in drawing process, they will not be able to share the load, right. So, that is the reason that we always use the concentration little higher than the critical concentration, so that we are able to compensate for any kind of disentanglement which occurs during the crystallization process. Not only this, even the economic reasons also favor this. If I have slightly higher concentration, that means my production would be slightly higher. Okay? So, the economics are also favorable at slightly higher concentration. Now, using the critical concentration, it is possible to achieve the ideal maximum draw ratio from the gel state. Here lambda max denotes the maximum possible draw ratio that can be achieved from the gel state. And as you notice over here in the formula, this maximum draw ratio is proportional to the inverse of under root of molecular weight and the inverse of under root of concentration, and it is proportional to C, which is a material constant, and it is different for different materials. It is a constant for a which varies with the material properties. So, what does this mean? This means the moment I increase the molecular weight or I increase the concentration, it is going to become more difficult to draw. The drawing process is going to become difficult. So, why is that? Very obvious. The entanglements are increasing in both the cases, whether you increase concentration or you increase molecular weight, the number of polymer chains or entanglement is increasing. So, then it is going to become increasingly difficult for drawing. So, as I said, the maximum draw ratio decreases with increased entanglement. Therefore, for every system, meaning for every molecular weight, there will be an ideal concentration from which you can obtain the maximum draw ratio. If the molecular weight is very high, then this concentration would be slightly lower, and if the molecular weight is intermediate, then this concentration would be slightly higher, right, because it has to take care of the entanglement degree. Now, let us look at, having understood the basic principle or concept of critical concentration and gel spinning, let us look at what are the main steps in the process of gel spinning. What do we need to do? So, the first step is I need to make a solution of the polymer. I can't spin it from the melt, right. I have to make a solution of the polymer closer to the critical concentration, little higher than critical concentration. Then the next step is I need to spin it. The spinning has to be done using a solvent which is appropriate, which would dissolve the polymer well, homogeneous solution, and after spinning it should be able to give a gel formation, it should give a gel like structure, and finally, the gel like structure should be suitable for high temperature drawing, right. So, these are the 4 main steps. Let us look at them one by one. So, when I am talking about the dissolution or the solution properties, so very often a molecular weight which is used is more than 10 lakhs or so, which is very high value, and the solvents which are used are decaline, paraffin, etc. These are all hydrophobic solvents. Polyethylene is hydrophobic, right. So, we all know like dissolves like. So, only hydrophobic solvents like these will be able to dissolve polyethylene. Another important point is polyethylene is not readily soluble at room temperature. You need to heat it. You need to heat it to around 100 degrees or more than that to dissolve it and get a homogeneous solution. The concentrations for about 10 lakh molecular weights are generally in the region of about 0.5 to 0.7 weight percent. This is just to give you a fair idea about what are the kind of concentrations which are used in gel spinning. You all know about acrylic spinning, right? Can anybody tell me what kind of concentrations do we use in the dope in acrylic? 23%, 24%. and here 0.5%. So, very different. The important point is the solvent which we select, it should be such a solvent that it dissolves the polymer at high temperature when we are making the dope, but at lower temperature, that means in the spinning zone, after the spinning, it should allow the polymer chains to crystallize from the solution very easily on cooling or removal of the solvent. So, this is a very specific requirement with respect to the solvent which is used. Now, how do we spin it? Do we use the normal spinning method? One typical method is you carry out the spinning in a manner like normal solution spinning, where the spin rate is not immersed, something like dry jet spinning. The solution is at a temperature of about 140, 130 degrees centigrade, and the fiber which is spun is passed through a cooling bath, a bath which contains another hydrophobic solvent, so that this hot fiber, when it gets immersed in this bath, it cools and some of the solvent is exchanged. That means, in the not really coagulation bath, in the cooling bath, the polymer is in the crystallized form, in the gel form. That means, some of the solvent has been removed. That means, polymer chains have begun to crystallize over here. So, in the cooling bath, we have the gel form of the fiber, which is the aspen fiber, which has residual amount of solvent in it, and this fiber is taken to high temperature oven for super drawing, and you will be surprised to know that the extent of drawing in this case is almost 40 times, 50 times, very high degree of draw. Unlike the normal fibers, unlike the normal textile fibers, where the draw ratio could be 5, 6 at the max, right. So, there is another method by which you can remove the solvent or you can carry out the spinning. In this method is something similar to the dry spinning method, wherein the polymer solution is passed through a heated chamber which has inert hot gas. So, when the fiber is spun in this hot nitrogen gas would help in evaporating the solvent, and when it evaporates the solvent, again it is inducing the crystallization of polymer chains, which indirectly means, what am I forming over here? Can anybody tell me? We have just discussed in the last method, right. It is the gel formation, it is the formation of crystallites. And now, this aspen fiber can be taken to a air oven and again drawn 40 to 50 times to the extent it is drawable to the maximum degree, and we get a drawn fiber which has super high strength and modulus, right. So, these are the two methods by which we normally carry out the spinning of PE gel fibers. You all must be wondering, I have been using the word gel, 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 and I guess you all know gel means what? Gel means a cross-link structure. So, here when I am saying gel, gel basically means the crystallites which are physically entangled and connected. So, if you have from the solution, when you spin in the aspen fiber, when the solvent has been removed partially in the gel form, you have crystallites which are connected by entanglements. Please note, the entanglements are not like melt spinning. There are only 1 or 2 entanglements. It is just to connect them. They are only forming a connection point, so that during drawing one is able to transfer the stresses from one polymer chain to the other, right. So, if I repeat, gel means the dispersed crystallites which are connected by a small number of entanglements, and they are also known as pseudo cross linking points, and such a structure is ideal for drawing. If I am able to form a structure like this, it would be ideal for drawing. Now, what kind of structure does it form? Let us look at the slide. The first part shows the gel, right. It shows the gel, that means I have the crystallites which are dispersed and connected with the minimum number of entanglements. As I draw, what happens? The folds open up, the polymer chains open up, and slowly all these crystallites get connected into lesser and lesser number of connected points, and they result in a structure which has highly oriented and aligned polymer chains along the fiber axis, which is shown in the last part of this drawing mechanism, right. So, this is what is super drawing. That means, I have drawn it to the maximum degree, no further drawing is possible, and this kind of structure is only possible when I have a lamellar structure in the S1 fiber. If I do not have a lamellar structure in the S1 fiber, I will not be able to get perfectly oriented extended chain structure like that. So, one by using this approach of gel spinning, one can suitably control the entanglements, regulate the entanglements, and get highly oriented defect free structure which can give us high performance properties. So, now having learnt about how this fiber is made, let us look at the primary properties which would ultimately decide the end applications of these fibers. The primary properties, as we were initially also trying to tune, are high strength and high modulus, and not to forget, polyethylene has very low density. So, these high strength, high modulus properties are in combination with the low density of the material. So, when I say low density of the material, that means the specific strength of these materials is much higher, right. So, if you recall, in the part 1 of this particular module, when I had shown you a particular slide where I had given the comparison of all the fibers, especially steel fiber and ultra high molecular weight polyethylene fiber, and I had shown you it is only because of the density that the ultra high molecular polyethylene shows much higher performance on the weight as well as volume basis. So, what we have learnt in today's class is actually what the scientists have achieved in half a century. They have taken nearly 50 years in converting or making suitable systems to convert regular polyethylene fibers to ultra high molecular weight polyethylene fibers. To summarize, I would say that they have tried to play with the entanglements, they have tried to understand the mechanism which is leading to high performance properties and suitably changed that, regulated it, regulated the extent of entanglements to convert it to highly extended structure which has minimal side chain defects or folds and which has resulted in these high end properties. Now, although the mechanical properties of polyethylene are excellent on weight basis as well, but it has one limitation, that is the melting point. The melting point of polyethylene is low, and this is one thing which we cannot do anything, because it is an intrinsic property of the polymer. If you remember, we said a material, a flexible polymer with inert chain, that means no interaction between the polymer chains, no interchain interaction. So, our requirement was to start with a material which has no interchain interaction. So, obviously, when the interchain interaction is low, the melting point is bound to be low. It is nothing which we can change, it is nothing which we can alter, right. So, it is actually a problem of the material itself. So, what is the possible solution? The possible solution I will be talking about in the next part of this module on new generation fibers. Before that, let us have a look at the mechanical properties of polyethylene fibers. Polyethylene fiber is commercially available under the trade name of Dyneema and Spectra. This table gives you the density, tenacity, modulus and elongation at break of different grades of commercial fibers produced by these companies. If you look at it, the density is less than 1, that means it floats on water. So, that means you can use it for applications where for ropes etc., for fishing nets, where you need high strength, high modulus, high mechanical properties, but the material is easy to use. The fishing net will be floating on the surface of the water. So, that means the usability is better, right. Not only that, polyethylene has got good stability, good environmental stability. It does not interact with water or salt water, it does not wet, it has no moisture regain, it does not absorb water at all. So, the properties of the material does not change when you use it in the sea water or in open environment or in sunlight. So, therefore, it can be used for such applications. If you look at the strength of these materials, the strength of the material is pretty high, 2.8 to 3.7 Newton per tex, which is almost equivalent to, no, that means in the range of 3 to 3.5 GPa, which is very high and very high modulus. And if you notice, it has a very low elongation at break. Can we think why it has a low elongation at break? It has low elongation at break because we have not left any folds at all. we have already extended it to the maximum possible degree. We have super drawn it. We have converted all the folds into highly extended structure. It cannot extend any further. We cannot stretch the chemical bonds, right. So, therefore, it has very low elongation break, and for that matter most high performance fibers, you will notice, we will learn in future, have very low elongation at break. So, with this I would like to complete this part of the module which was related to PE gel fibers, and in the next module when we talk, we will look at how are we able to overcome the limitation of PE gel fiber by choosing some other alternate material which is intrinsically better, intrinsically not flexible, rather rigid structure, and how are we able to convert those to high performance fibers, what are the strategies, and how does that compare with polyethylene, right. So, thank you.